Poonam will do a session on modeling stochastic programs. But I'll do one of the problems here, if you can read it. You make it a little bit bigger. Okay, so here's the problem. Okay, so that it says we have a plane, and the plane has 200. It has space for 200 economy seats. So if you put economy seats in the entire plane, you could get in 200. But you can also divide the plane up into different sections. So you could divide it, for example, into a section for first class, and every first class seat takes up 2 economy seats. You could also add a section for business class, and every business class seat takes 1.5 economy class seats. There's a profit, so the profit on a ticket is 3 times higher for first class as it is for economy. And a business class ticket has a profit that's 2 times as high as it is for economy. Now, the way this works, once you set up the plane, so once you decide how many seats are in economy, how many in business, you can't change it, even though you might have different demand. So this part says, these are the decisions you have to make now. So that's like the first stage decisions. So the first stage decision will be, how many seats do I put in the plane for economy, how many seats for business, and how many seats for first class? And then they're planning for what might be the demand. And so it says, make my screen come alive. No. Turn. Okay. So they have 3 scenarios of demand. So the demand is either weekday, morning, evening, weekend, or weekday in the middle of the day. And they say, under the first scenario, they're 20 first class. They could sell 20 first class, 50 business, and 200 economy. Under the second scenario, it's 10, 25, and 175. And then under the third scenario, it's 5, 10, and 150. And they cannot sell any more tickets than seats in any of these sections. Okay, so the decision is first to decide how many of each class of seat you're going to put in the plane, and it has to sum up, can't be more than 200. There are only 200 spaces if you put in all economy. And then there's like the second stage decision, which is how many tickets am I going to sell in each of these seats, in each of these seat areas. And then that's the random part. That's the part where I don't know it ahead of time. And then, so the decisions in the second part will be how many seats we sell in each of these different parts. So the first, okay, so the first stage is going to be the number of seats in each class. Okay, so we might have XF for first class, XB for business class, in, let's say, XE for economy class. Okay, so we have first stage decision is how much am I going to put into each of these different areas. The second stage decisions are going to be how many tickets do you sell? And it's going to be under each scenario, and there are 3 scenarios. The scenarios are 1, 2, or 3. Okay, so the second stage is the number of tickets to sell under each of the scenarios, 1, 2, and 3. All right, so this would be, let's call it Y first class under 1. Let's say this is I for 1, 2, or 3. Business, 1, 2, or 3. And economy, 1, 2, or 3. All right, so this is tickets. Tickets sold in first class under scenario 1. And this is tickets in business under scenario 1. Or under scenario 1. And then this is tickets in economy. Under scenario, I guess I have scenario I here. So I is 1, 2, or 3. Okay, and I is 1, 2, or 3. Okay, so those are our, let me just put this up for a minute, and then we can I, maybe I'll just block it. Yeah, just to dim it. No, oh, you know what? I can just, oh, okay. Okay, so first stage, we make this decision. The second stage, we make the second decision. And now we can set up the problem. So the problem is, what do I want to do? I want to minimize the expected value of the first stage decisions plus the second stage decisions. In this case, I don't think there's any cost for the first stage. So the cost for X is actually 0. So I'm not going to have any cost for putting in the seeds. And then I'll say, okay, subject to what constraints? Well, the constraint here is that I can't use up any more than the total number of spaces. So there's a constraint that says that this XF plus XB plus XE so XF took up 2.5 spaces. XB takes up 1.5 spaces, and XE takes up 1 space. And all of that is less than or equal to 200. That's how many spaces I had available. Okay, now, the recourse part of this is that there are these 3 scenarios. So we could say this is plus 1/3 that's going to happen for each of the 3 scenarios. Now I'm going to sum over each of these 3 scenarios. That's i's going from 1 to 3. And now the revenue I get, the revenue is 3 times as much for the first class and it's negative because it's revenue, so it's going to be, I would maximize expected revenue. Here I'm minimizing the negative of expected revenue. So minus 3 times the first class, minus 2 times the business, and then minus 1 times the economy. Okay. And now, these have to be constrained as well. And what should be true is that the first class seats are no more than the demand for first class under each of these. The business class seats are no more than the demand. This is the demand. For first class under scenario I. The business class is no more than a demand under scenario I, and the economy class is no more than the demand under scenario I. But they're also constrained by the number of seats in the plane. You can't sell any more than the number of seats. So I also have a constraint that says each of these is less than or equal to the x that I determine in the first stage. So it's like this part is the first stage, and this part over here is the second stage. So I can't sell any more than the first class seats I put in. I can't sell any more than the business class. And I can't sell any more than the economy class that I put in the plane. And all of these constraints hold for I as 1, 2, and 3. And then the x variables are all non-negative, and the y variables are all non-negative. Okay, so this has the form of the stochastic program. So the stochastic program says we have a set of first stage decisions, we have a set of second stage decisions, which depend, these are going to depend on what I do in my first stage. And then the optimization model is you minimize the cost of the first stage plus the expected cost in the second stage, where the second stage meets a set of constraints that here depend on the realizations of the demand and also depend on how much capacity you've installed in the first stage. Okay, so that's an example of a stochastic program. So we have first stage decisions, then we realize the demand, we get to observe it. Customers arrive, they demand seats in the plane. We can sell seats up until our capacity, and then once we've sold the capacity, then that's done. And then that's what these constraints allow us to do. They tell us, okay, we can only sell the minimum of the capacity and the demand in each of those scenarios. Okay, any questions on the? Yes, because this is the revenue number. The revenue number for this is, or profit number is 3. So I would like to maximize revenue, but because I did it as a minimization problem, I minimized the negative of the revenue. Okay, any other questions? Okay, so I have some other problems like, yes. Oh, it's just 0. I just to show that there's no cost to put in the seeds, so it's 0. I just mean 0 times x. Yes. How are they connected? They're connected through these constraints. So I make this decision here for the installation, and then that constrains how much I can sell in the second stage. So I set up the number of seats in the first stage, and then that constrains what I sell in the second stage. Okay? Okay, that's, so now let me go back and I'll go through the other things that I have on these models. Okay, so as I say, I have a number of other exercises like this that you can go over this afternoon. Yes? What? Yes. Yeah, so these are decisions. So, yeah, so they're not, they're just multiplying the matrix. So they're just variables that multiply by the matrix that determines the constraints. Yeah, so they multiply by those coefficients. Oops, let me get my password. Okay, so I actually, I also have, actually, I'll put this on the thumb drive as well. I have these set up in Excel. So this is the formulation of this model in Excel. And I have, the blue are these decisions. So this would be how many first class, business class, and economy class seats. And then this is totaling it and then making the total less than or equal to this limit. And then these are the number of tickets that you sell. So these are those y variables. Scenario 1, scenario 2, scenario 3. And then I've totaled the profit over here. And then this is the expected profit here. And so if I have this set up so that you could solve it in Excel. And so for example, if I use the solver here, yeah, and this is set up to, so this has already solved the problem. But this solution up here is with all these 3 possible scenarios. And then I get this value of 208. And then what I've done down below it is to put in the expected value. So I just put in the average of all of these. So that's like 11.67. That's 28.3, 175. And then you would get this value down here and make this decision up here for the number of seats. So you see that the optimal decision actually, again, has this characteristic that it does something different from what the expected value solution does. Okay, so let's go back to the, oops. I want the other one. Okay, so what I'm going to cover in these, the rest of this lecture will be about, mostly about those objective functions. So in this case, what I did is I just had the expected value. That was the objective. I didn't include anything for risk. But often what you like to do is to put risk into the model, so somehow reflect how risky a decision is. So I'll talk about putting risk into the models, and including integer variables. I'll give an example. And I'll show you that sometimes, often, it makes it harder to solve a problem when you have uncertainty. So many problems are harder to solve with uncertainty, but in some cases, it can be easier to solve a problem. So I'll show you an example. For example, if you solve the deterministic problem, it's an NP hard problem. It's a problem that there's no efficient algorithm for. But the stochastic model is actually solvable. It has a polynomial algorithm. So sometimes you can have a problem where you add uncertainty and you turn the complexity from NP, from a hard problem, to a problem that actually has polynomial complexity. So I'll talk about those advantages that sometimes occur. And I'll give one computational complexity kind of result for stochastic programs. Okay, so what I'm going to talk about are risk measures. So risk measure is something that reflects a value in the objective that is due to risk. So due to how much variation there is in the outcomes. And we talk about certain kinds of risk measures that are called coherent. So coherent risk measures have the following properties. They're convex, so they're measuring risk. So that means the more risk there is, the worse the risk measure is. So the value goes up. So they're convex, and well, if I have more, like if I get more return, then these risk measures actually go down. So they're convex and decreasing. They have a property that if I add in something for certain, then that subtracts from the amount of risk. So you could think of this as this risk measure is like a security amount, an amount that I need to keep to guard against losses. So I want to put a certain amount in to guard against losses. If I have more available, then I need to put less money in to guard against those losses. So this property says if I put in a certain amount, then that should just subtract out exactly from how much I have to put in. The other thing is that they scale. So if I need to put in lambda, or if I need to put in r of lambda times whatever that risky result might be, then my risk measure should just be lambda when lambda is greater than or equal to 0, lambda times that amount. Okay, so this is, these are risk measures for gains. So if C is a loss, then these would be the negative of that. Now, risk measures are related to utility functions and von Neumann-Morgenstern utility functions, or rational utility functions. Those rational utility functions have these properties. So that means they're complete. That is, you can always judge whether one outcome is better than another according to a utility function. They're transitive, so if A is preferred to B, B is preferred to C, A is preferred to C. They're continuous, meaning that you could always find a utility that's between A and B if A is preferred to B. Monotonic, the more you have of something that is desirable, the better. And then what is called substitutability, that says if I add in something that's irrelevant, it shouldn't change the ordering. So if I have C is irrelevant for A and B, if I have A plus C, that should still be better than B plus C. All of these things actually imply the same. Well, actually, it implies concavity of the utility measure, so it implies a convex relationship. But these are desirable, but it's not clear that they're always what people actually believe. Some of the things that I talked about yesterday, like the robust optimization model, that's the maximum of the possible outcomes over whatever this criterion function might be. That may not have all these properties. So for example, if I take this maximum here, this is the maximum over this set. So this is like the ball of radius epsilon. So if C is just a sphere, and I maximize C times x minus b over that sphere, then the result is I'll get the radius of the sphere and then the norm of whatever this vector might be. So this by itself is actually not a coherent. It doesn't obey those properties. However, if you make x relative to b, then you can make it into a coherent measure. This one, if I just take, it's just the maximum of c less than or equal to x, so that's just the minimum of c and x. Well, that's not going to be coherent as well, because when the minimum is just c max, it's not going to change with x. So if I add in a constant, it's not going to change it. So that would mean it doesn't obey the coherent property. So many of these measures like this robust optimization measure, they may not have coherence, and that means that they may not have convex formulations. What's nice about the coherent risk measures is that there's always a way to write them down as an optimization model. So coherent risk measures like that, if R is a coherent risk measure, you can always write it down as the supremum over a set of probabilities. So Q here is a set of probability measures of the expectation with respect to that probability measure of this random value C. So coherent risk measures, because they always have this representation, you can always make them, well, this is always going to be convex, because it's the maximum of a set of convex functions, maximum of a set of linear functions. So the maximum of a set of linear functions, that's always a convex function. So we have, this is always going to be a convex function because of this property here. Now, a couple of things. The risk measure that is often used is called value at risk, or VAR. And value at risk is defined this way. It's the negative of a value t such that the probability that your outcome is less than or equal to t is at least alpha. Or another way to look at it is it's the negative of the alpha quantile. No, oops. Let's draw a picture of that. So if this is like the density of C, if the probability down here is alpha, I'm going to make 0 somewhere else. Make this 0. Okay, so let's say this point is T. Okay, so T is F inverse of alpha. So this is the alpha tail. Then the var is essentially minus T. So the var of alpha of C is minus T. Okay, so it's how much I could lose. T is a negative number, so I could lose minus T. Okay, now C var is the expectation of, it's the negative of the expectation of everything up to the var. So C var is the expectation of this tail. Conditional expectation over the tail. So if I take the conditional expectation over here, that's the C var, or conditional value at risk. Okay, so I have a measure here, which is like this alpha quantile. And I have this other measure here, which is the integral of the alpha quantile, the integral over that tail. Now, it turns out that C bar can be represented this way. It has a representation as the infimum of a minus T value plus 1 over alpha times the expectation of T minus C, the positive part. Another way to think about it is it's the distribution that essentially gives you the lowest possible value if you assign a measure of alpha to some part of this distribution. So where you would put that alpha would be wherever it has the lowest part. So it's the distribution that gives the measure 1 to a probability alpha region that has the lowest possible value. And that makes it a coherent risk measure. Now, coherent risk measures are related to stochastic order. So we say, in terms of stochastic order, x is stochastically greater than y if the probability up to any number t under x is less than or equal to the probability up to any number t under y. In other words, that the cumulative under x is always less than or equal to the cumulative under y. That says that x is greater than y. It's because the probability of being less than any number is smaller for x, which means probability of being greater is always greater for x. Now, you can define different orders of these risk measures by saying, I'll take the expectation of let's say, not just take the expectation of the cumulative to get the second order. So I take the cumulative distribution of x and then take the expectation of that. Or I could take the expectation of the thing that I get from taking the expectation of the cumulative. And we say that random variables are ordered in that kth order if, when I take this kth order cumulative, if I take the kth order cumulative, that's less than or equal to the kth order cumulative of the other. So the kth order cumulative of x is stochastically greater than y in the kth order if the kth order cumulative of x is always less than the kth order cumulative of y. That's equivalent to saying that the expected value, well, stochastic dominance is the same as saying that the expected value of anything non-decreasing, in other words, anything increasing, is always greater in x than it is in y. This second order stochastic dominance says that it's always the x is going to be second order dominant over y if the expected value of any utility that's both non-decreasing and concave is, and this is just saying that it has a mean. As long as its expectation is non-decreasing and concave, it's greater than or equal to y. So what this says is if you have second order dominance, it doesn't matter what utility function you have. If x is always second order dominant to y, for any utility function that has these properties, non-decreasing and concave, x would always be preferred to y. So if I can show that something's second order dominant, then I can show that it's always preferred. What that says is for coherent risk measures, because coherent risk measures have this property, they're non-decreasing and they would be concave if I'm subtracting them off. So in other words, if I want to maximize and I subtract off a coherent risk measure, I'm going to get something non-decreasing and concave, and therefore I know that I would like better things to have higher expectation than smaller things. So second order dominance always would order coherent risk measures the same way. So if I ever can show that something is second order dominant, then I would show that I optimize with respect to all second order, or all coherent risk measures. So these tail expectations, those are like the C-var, that example over there. Those tail expectations provide the same kind of ordering as second order stochastic dominance. So another sort of motivation for these coherent risk measures is that they preserve this second order dominance, or they can't contradict second order dominance. I should say that there are certain criticisms of these coherents. So this paper that I cited here by Ko, Peng, and Heidi, it says there's a part of the assumptions that I had for coherent risk measures. One of them was subadditivity, that if you add coherent risk measures together, it's less than or equal to the sum of those. Add two random variables together, any coherent risk measure is less than or equal to, of the sum, is less than or equal to the sum of the risk measures. They say, well, that doesn't always make sense. It makes more sense if you restrict it to when x and y have a property called comonotonic, which says that they sort of move in the same direction, that x of any event omega 1 minus x at any event omega 2 times y of any event omega 1 minus y of any event omega 2. They're always greater than or equal to 0. So that says whenever an event is better for x, it's also better for y. As long as they have this property, then they have this subadditive property. So they say this is a more natural thing. If you don't always have this property, this comonotonic property, then it could be that there are times when x and y are moving in different directions, and they're not giving you consistent results, and therefore you shouldn't expect that you get this subadditive kind of property. You shouldn't expect then, if I break them apart, that I'm going to have more risk with summing x and y separately than I would with summing x and y together. Okay, so they say this is a better property, and there's certain kinds of risk measures that include var. So var, that risk measure here, actually satisfies this property, even though it doesn't satisfy the coherence property. Okay, this is just to show that this risk measure that comes up, there are these criterion for bank holdings given by Basel III that set up requirements for banks for how much capital banks have to keep on their books. And they're measured against the bank's calculation of its risk, its value at risk, this measure here. And so that their capital requirements are that you take the value at risk that the bank has calculated, you take some external measure, you take what value at risk it had calculated in the past 60 months, and then you take the value at risk measured against particular situations that are stressed, like the financial crisis, and whatever valuations that had in the past. It turns out that this kind of risk measure that's in these Basel requirements is what they call a natural risk statistic, which has all these kind of properties, including the fact that it has that property that I had in the last slide, this comonotonic subadditivity. One thing that this also has, if I sort of move around the set of samples that I use for these calculations, it's not going to change anything. So it has a lot of good properties. Bottom line is, we can put different things into our objectives. It's good if it's consistent with stochastic ordering. You'd like it to be consistent with stochastic ordering. And you'd like it to be consistent with at least this comonotonic subadditivity, that when two random variables move in the same direction, that risk should go down when you put them together. All right, I think I'll skip going through the natural risk statistics. Okay, now the question about this could be, are they actually the way people make decisions? And I'm not going to talk about this too much because the way people make decisions doesn't always obey these properties. Like, people may prefer things for different reasons. In particular, like if you look at Kahneman and Tversky's prospect theory, people don't necessarily have concave utilities. They don't always believe that a combination of two random outcomes, taking a convex combination of those is, let's say, worse than, or having the values at convex combinations is worse than having the value of a combination of the outcomes. So what their prospect theory says is that utility is something like this curve. If I'm too far from a target, then I don't value being further away too much. That I kind of have some sort of limited loss. That the further I am away from a target, it doesn't really matter so much. If I'm really far away from it, that doesn't seem to make that much of a difference. As I get close to the target, it makes a big difference to get to the target. But as I get above the target, I'm sort of satisfied. And the difference doesn't mean as much. So instead of just having concavity, which would be up here, which all the risk measures I talked about had some kind of concavity associated with them, instead of having concavity like that, it could be that you're in a situation down here where it's more like convex. Now, if I think about it from this perspective, and this concave part, that's more like the traditional expected utility, whereas if I'm down here, it's almost like you're, if you're down here, you would have a completely different kind of utility. To think about robust optimization would say that there's some utility up here, and any possibility of a bad outcome is going to make you have a really low result. So you're sort of putting, like, even for any small probability, you're putting a very, very negative value on any of those outcomes. But that can be consistent, because that's like saying, oh, well, I don't really care if I don't make the goal. I'm really far away, whereas if I get to the goal, I feel much better. So you could think that prospect theory has some elements of expected utility theory, or you could sort of extrapolate it to saying it's a little bit like robust optimization if you take it to the extreme, that down here I just don't care, and up here I get my value. Okay, so from that perspective, in terms of just the way people make decisions, both of them might apply. And as I said, having a competitor somehow sort of brings them together. And yeah, usually people are just misinterpreting when they say that there's some kind of paradox in what they say. Yeah, I think I'll skip this one as well. Okay. Yeah, just to kind of summarize this, I started off, I said risk neutral. If I just have risk neutral, just take expectations, just take the expected value. That makes a lot of sense when things are repeated a lot. It certainly makes sense in financial models, because if I have a complete market, I can always adjust the probabilities so that I just use risk neutral. So if you've done option pricing, you can always change the probability measures and then just use risk neutral, just take expectations. So with complete markets, you can always just take expectations and then discount. And oftentimes you can get the distribution. You could even get the distribution from maybe some properties of the model. So risk neutral applies in these situations that are well behaved, like either repeated very often or you have well behaved markets. The traditional expected utility, if you can define the function and the market's not complete, then that is you have some values that are not represented in a market, like they might be values that are particular to an individual. Then those traditional expected utility makes more sense. The worst case kinds of results, robust results, or like VAR kind of results, they're useful when you have limited information and you know that it's only survivability that counts. So if it's only the fact that you have to meet a certain target that really matters, then these models make a lot of sense. And then, like I said, if there's competition, and then looking at competition in different areas, they can be consistent because they can give you anything from risk neutral to a worst case. However, we can often have approximations that give guaranteed bounds. So even when the problems are hard, there may be approximations that give guaranteed bounds. And even in practice, there may be problems that you can solve, even though computationally you could say that there are cases that are as hard as solving anything else. Okay, so for stochastic programs, the same kind of things you can use for integer problems as you might for a deterministic problem. That is, you can use branch and bound. In other words, solve a relaxed problem and then branch on any fractional variables. You can add inequalities. Use all the kinds of things that you can use in deterministic programs. You can apply to stochastic programs as well. However, as I said, the complexity of these problems is almost always hard. So in general, it's at least as hard as finding the expected value of this recourse function, because the recourse function is q of x and the random variable c. The expected value of that is necessary in order to solve the optimization model. But it turns out, like in this paper by Dyer and Stauge, that this is actually even harder than NP. These are called p-sharp hard problems. P-sharp or sharp P. Sharp P problems. Harder than NP. It's the problem class of computing a function value that's the number of paths for a non-deterministic Turing machine running in polynomial time. Yeah, but the one thing is it's always at least as hard as NP. It's at least as hard as NP because it's the number of ways that you could possibly solve an NP problem on a non-deterministic Turing machine. Okay, so in general, these are very hard problems. However, and this is in an old paper of mine with Hans Frank, John Mittenthal, and Alexander Renoy-Kahn. There are some problems where randomness actually makes the problem easy, where if I didn't have randomness, the problem would be hard. So here's the situation. I have a single machine, and I have a set of jobs, and I know the processing time. So each of the jobs has a different processing time. And my goal is to minimize the average completion time of the jobs. So if there was nothing else going on, what I would do is to order the jobs by shortest processing time. And I do the shortest jobs first, and order them by processing time, do the shortest one first, and then do the next shortest one, and so on. And that minimizes the average completion time. So shortest processing time first is easy when the machine's always available. However, suppose the machine can break down some point before I process all the jobs, before the sum of all the processing times. Well, that means it's going to disrupt some of those jobs. It turns out if I knew, even if I had deterministically known, if I tell you when the machine's going to be down and I fix when the machine is down, that problem is NP hard because it's like a bin packing problem. You're trying to pack as many jobs as you can in before the machine breaks down and then complete jobs after the machine is available again. So that deterministic problem is NP hard. However, suppose the machine breaks down at an exponential rate. So it has the memory less property. If it breaks down at an exponential rate, it turns out, again, that problem is easy. So if the machine breaks down with a Poisson random variable, in other words, the rate at which it breaks down is exponential, then that problem again is solved by the shortest processing time schedule. So it's the random problem is easily solvable, polynomial, in fact, log n of the number of machines, n log n. But in the deterministic case, it's actually an NP hard problem. So there are some cases where randomness, because randomness kind of removes the complexity, it sort of smooths out. The complexity in this case is all about trying to pack things in. If I don't know where it's going to be, I can't pack things in. So sometimes the randomness actually gives you more flexibility, and you actually can solve problems that you couldn't solve otherwise. Okay, I'll do this example from Swami and Schmoy's that shows how you can approximate problems, how you can sometimes approximate problems that are hard otherwise, but you can often come up with approximations that are relatively easy to find. Okay, so let's say there's a random demand, and I want to satisfy that random demand. But I'm trying to, it's kind of a setup like I had before. I have to set up my capacity. I'm going to set up capacity in different places. Random demand is going to arrive, and then I'm going to try to satisfy that demand from my capacity. Okay, so I'm going to, first I make some advanced decisions, like I put in the capacity, like I put in the number of seats on the plane. Then there's going to be a realization of some random event, and then I'm going to take some action. So then I'm going to do this recourse action. And then I may pay a cost for taking that action. So I'll have my stage one. In other words, I'm going to take those first actions, and then I'll have my expected value of what I do in stage two. Okay, so here's the situation is I have a set of clients. These are the clients, the Ds, the set D, the green dots. And what I'm going to do is to set up locations at different places. And what I want is that if this client needs demand, I'm going to be able to satisfy that demand from this location. And if this one needs demand, I'll satisfy it from this location. But I have some constraints. So, for example, I might not be able, if demand was over here, I might not be able to satisfy it from here. So there's some constraint that says there's only some set of these clients that I can satisfy from each of these locations. And what I'd like to do is to minimize the cost of installing locations to satisfy the demand at all of these clients. Okay, so I open some facilities, like these are the facilities I put in. I open those facilities and I pay for their costs. So I pay that up front. So that's like installing the seats on the plane. I pay to put in some of these facilities, and then and then I'll realize demand, and then I'll be able to satisfy the demand. Okay, now the probability distribution. So the clients are going to have a set of possible scenarios, and there's going to be, let's say, I'll assume independence. So independent probabilities that every client is going to want, or any client is going to want demand. And I assume I can sample from these clients. Okay, so in stage 2, in order to meet the demand, I'm going to see what clients could be served from each of these. Now, it could be that, let's say, these 3 clients could not be served from the 2 that I had originally put in. Well, the setup for this model is that I have to serve all the clients. So in order to serve these clients, I'm going to have to open up a new facility. So I open up a new facility in the second stage, but in the second stage, it's going to cost me more. So I have to pay to put in the facility. Then I also have to now I have all these facilities that can serve all the clients, and then I may have to pay to actually serve each of the clients, and then I may have to pay based on the distance to each of these clients. Okay, so the stage 1 here is where you open up the facility, and then stage 2 might be some additional facilities you have to put in order to serve some of the clients that are not yet served. Okay, so the scenario here is represented by the clients that you actually have to serve. And as I said, you may open these additional facilities in order to serve those clients. And if you do so, you pay a cost to do that. Okay, so these are the facilities that I open up, and then this would be the cost of serving the clients. Okay. So the overall cost is the cost of installing facilities in the very first stage. And then here's the recourse is for each set of clients that shows up out of the set of possible sets of clients who could show up, what's the cost for meeting their demand? Okay, so there's certainly different outcomes or different solutions that you could try. So one of the solutions would be that you open facilities everywhere, and you're guaranteed that there's at least no facility costs in the second stage. So you could plan for everything, or you could decide not to have any costs up here. You could decide to defer all of your decisions to make after you get to observe what the demands are. So after you get to observe A, then you'll just optimize in that case. Now, of course, both of these could be bad. The idea here was to give an algorithm that guarantees a certain amount, guarantees that you're close to an optimal solution, that you're close in some sense. So it guarantees optimality up to a certain level. Okay, so that's an approximating algorithm. So what we want is an algorithm that will work well on any instance of this problem, and for any probability distribution. So in other words, I could have any kind of facility costs, any kind of costs to serve the clients, and any kind of distribution over where the clients might be. So it turns out again, so in general, this is an example of, like I said, those sharp P problems. So we know that just solving the expected value of the recourse problem, we just know that that part is sharp P hard. So to have an optimal algorithm for this, we know is not going to be possible with just a polynomial algorithm. There's no polynomial algorithm that should be able to solve this optimally. So that means that we have to solve it approximately in some way. So what we would like, I mean, if we're going to solve it approximately, we want at least to make sure that it's an algorithm that works in polynomial time. So we want to find a polynomial time algorithm that is going to give us something that's near to the optimal solution. The concept here is an alpha approximate algorithm. So that's an algorithm that's always going to guarantee, well, A, it runs in polynomial time, but it guarantees that for any instance of the problem, you're within an alpha factor of the optimal solution, the minimum cost. So if the minimum cost is opt, then you're always within alpha of opt when you solve this problem. This alpha is called the approximation ratio of this set of this algorithm. Okay, so we want to get an algorithm that guarantees us this kind of behavior. Okay, just to give some background, this paper has an approximation algorithm for one kind of resource provisioning model. Ravi at Carnegie Mellon, he has a number of papers in this area. Here's another set of papers with proportional costs. Here's a kind of a specific kind of paper. Now I'll talk about Swamy and Schmois's result. So theirs is for two-stage stochastic integer optimization models, no assumptions on the costs, and it's a fully polynomial scheme for these two-stage stochastic linear programs. So it will give a fully polynomial approximation. So it allows for reducing stochastic optimization problems to a deterministic problem that guarantees a given kind of approximation. And so now, I'll show how this works. So it starts by saying, or starts by observing that if you have a solution to a linear program for an integer problem, well, we're going to assume that the linear program can be solved in polynomial time. So if I can set it up with linear programs, then I know that I can solve those in polynomial time. So I'd like to have an algorithm so that the base of it is something like a linear program. So we'd like to be able to solve linear programs in order to be able to get our solution to this stochastic program. What I'm going to assume is that it's a particular kind of linear program. So there are classes of linear programs for which I can find alpha approximation algorithms to round them to the closest integer problem. So I'll take the deterministic linear program. If I can round the deterministic linear program solution and get within alpha of the optimal solution, then that would be an alpha approximation. So I'll assume that there's an alpha approximation algorithm to the linear program. Okay. So that's the basic building block. So the basic building block is I start with the linear program and then a way to round the linear program. Okay, so now here's what we can do for this example here. I can say, well, let's say I have an optimal solution let's say I have an optimal solution to the original problem. Then what should be true in that optimal solution is, let's say my optimal solution is given by a set of facilities X in the first period and then a set of facilities that's installed in the second period Y. I know that I have to cover all of the facilities that for any outcome A of clients that are seeking demand in that second stage. Okay, so I know that for any of the possible sets of clients, I must have that for each of the facilities or each of the clients that's being served, so this would be a client that's actually being served under a client that can be served by S. I have to have, for each of those clients that I've either opened up, I either have that facility being opened in early, or I've opened that facility late. So in other words, I've either done it in the first stage or I've done it in the second stage, but in either case, I've covered that client. So for each of the clients that's actually seeking demand, this would be the set of facilities that that client for which that client can be served. One of those has got to be 1. Oh, so in the optimal solution, I know that one of these is 1. For each of these possible realizations, what that says is either this part is greater than or equal to a half, or this part is greater than or equal to half, because the two of them have to sum up to something greater than or equal to 1. So that means one of these two things has to be greater than or equal to a half. So if I take 2 times, it, I know that 2 times this has to be a total cover for the set of all of the facilities that might, or all of the outcomes of the facility. So element here refers to a set of outcomes. So for every possible set of outcomes, I know that I know that I have an x here, such that 2 times x is going to give me something that's got to be greater than or equal to 1. So that means that 2 times x is always going to be greater than or equal to 1. So 2 times x is a fractional cover for the set of all these possible outcomes. So that means if there's, that I should be able to round any of the integer set covers at a cost that's at most 2 times x. So if I have any integer set cover, then I should be able to round it at a cost of at most 2 times x. So the result is that I can, because I know that this optimal solution has to cover all of these sets, I know that this part of the optimal solution is at least a half, that I can solve the fractional set cover problem and then be able to double that and cover all of the points. So I can always go from having, if I can get an alpha approximation of, let's say, the deterministic problem, then 2 times that is going to give me a solution to the stochastic problem. Okay. So let me summarize the things I talked about here. So we had, I went through the objective in the stochastic program, and I said that we have some kind of utility or risk. Often what we'd like to do is to have that utility or risk satisfy a given set of axioms. So the axioms generally refer to things like, if I have a stochastic order, if I say that this thing is stochastically better than this other thing, that my utility function should say, oh, the utility of that first one, the greater one in stochastic order, is greater than the utility of the second one. That's something that is satisfied by this set of risk measures that are called coherent. Those coherent risk measures include the conditional value at risk, this conditional value at risk over here. Because the coherent risk measures have a representation that's the maximum over some probability that, like this is the maximum over this probability that has the lowest values. Because it's the maximum over that probability set, they have this convex formulation. In other words, they're the maximum of some linear function, of a set of linear functions. That means that they have a convex formulation. And that convex formulation allows you to put it into a single optimization model and have it be convex. So coherent risk measures naturally lead to convex formulations. Although coherent risk measures always give you convex formulations, they may have issues for calibration, particularly to people's behavior. That is, that people's behavior may violate some of the convex relationships because people have this prospect theory kind of preferences. That is, if I'm very far from a target, I view that as less important as if I'm close to that target. So because of those preferences, we may observe behavior that's not consistent with convex utility function or concave utility functions. So when we try to look at these things from data, we may not see things that are consistent with our convex models. So our convex models may be ideals, but they may be ideals that are not present in you know, actual empirical observations. Okay, so those were the issues about the utility functions. Now, in terms of both to eliminate convex, or to eliminate or allow problems that are non-convex, and to allow for problems like those facility location problems, where the decisions involve integer variables, whether I put in a facility or not. In general, those problems, and in particular, stochastic problems that involve integer variables, in general are very hard. In general, they're at least NP hard. So they have at least the complexity of something that's NP hard. However, there are some special cases. So in special structure problems, like that scheduling problem, it may be that randomness, particularly when it's unpredictable, and it's because everything is so unpredictable, that it may be that a simple solution is best. So when things are very unpredictable, like the machine breaking down at any random point in time, exponentially, where I can't predict when it's going to break down, if I can't predict it at all, then you can revert to simple solutions. So it could be that simple solutions actually become optimal in some of these random cases, depending on the structure of the problem. So for specially structured problems, whoops, I didn't want to do that. For specially structured problems, what should I do? Let's put it back up. Okay. For specially structured problems, it may be that even though the deterministic problem is NP hard, it could be that the stochastic problem is actually polynomially solvable. Now, in the case when there are provably hard problems, there are situations where you can come up with approximations. So you can come up with approximations for these stochastic programs in cases where you can do some kind of, or stochastic, in particular for stochastic integer programs, for cases where you can do some kind of adjustment, some kind of rounding scheme for the linear programming solution that produces, in the deterministic case, produces an integer program solution. Usually what happens is, if I have a way in which I can approximate the linear programming solution with an integer programming solution, that I can do the same thing in the stochastic model. In that facility location case, it turns out the worst thing that I can do is it'll double at least the relative cost. So if relative cost was alpha, it'll be 2 times alpha. So I should be able to at least get within a bound that's twice as bad as the bound that I have with the deterministic model. So for stochastic programs, you can often use what you could use for the deterministic model to make it into make it from a continuous relaxation to an integer problem. You can do the same thing for the stochastic model and essentially do it twice. So then doing it twice, you get twice the bound. So you can obtain these approximations that are guaranteed to give you a result within some error of an optimal solution, even though it's with a polynomial algorithm, even though it's a provably hard problem to solve. So this is an area where if, like for research, this is, Yeah, this is an area where I think there are a lot of different results because there are a lot of different structures of problems that you can look at from this perspective, where I know that there's a way I can solve the deterministic problem. If I look at the stochastic problem in a particular way, I know that I can adjust the deterministic solution in such a way that I get a solution for the stochastic problem. And that gives me another bound for the stochastic problem. Okay, so those are parts about the two-stage algorithm, so the two-stage models. So the utility functions and integer variables and complexity. And then what I'll talk about in the next session will be the multi-stage models. So multi-stage models, I'll also talk about continuous time and how stochastic programs relate to the continuous time optimality conditions like the Bellman equation. So I'll go through the Bellman equation and continuous time for the next session. Okay, thanks.